Thank you everyone for coming. My name is Martin. I work for Cake Solutions in New York. We're a consultancy. We do consultancy around Scala, Akka, Spark, Cassandra, Kafka, and many other technologies in the distributed systems, big data, machine learning world. As you've probably noticed, that the importance of data analytics is increasing in recent years. It's also the reason why we are at this conference. But current state in many companies is that they're using destructive updates, so they don't keep history of the data. They use analytics tools with poor scalability and integration. It's often manual process with slow iterations, so it's not really suitable for large amounts of data and fast data. But we often need to process large volumes of data really quickly, often in streaming manner. One of the options is to utilize parallel computing. There are many different programming models for parallel computing. Another level is distributed computing, where we have multiple machines working together, trying to reach a common goal. But distributed computing is often misused. It introduces many new complexities that may not be necessary for your problem, including having to worry about concurrency, time order, message delivery, network latency, and so on. Even large companies like Baidu or Google reportedly use GPU-optimized algorithms to run their most computationally expensive queries. And as you can see, single-threaded algorithms are often better performing than distributed systems. But on the other hand, distributed systems have many positive impacts, including availability, resilience, geographical distribution, ability to run on cheap hardware, scalability, or just the ability to scale. Today, large data sets just wouldn't fit on a single machine. Distributed systems are largely about trade-offs that must be carefully considered. Even with all those aforementioned complexities, some distributed systems have amazing performance. A good example is Apache Spark that won the Daytona gray sword of 100 terabytes benchmark or distributed databases. When developing distributed application, we really need to focus on two levels of optimization. So we need to optimize on single machine, so things like algorithms, register locality, cache locality, in memory or disk storage layouts, data formats, garbage collection optimization, and so on. And at the same time, the optimizations at the distributed level. So things like data locality, communication pattern optimization, failure handling, network traffic, and so on. Also, data processing pipeline does not consist from a single algorithm that we can optimize for GPU. It has to cover the whole life cycle of data. So from loading the data from external sources, running some transformations on the data, training machine learning models, running those analytics and data mining machine learning algorithms, and finally storing the data somewhere, again, in a database. So we need many technologies working together. I will talk mostly today about data processing, but there are also data stores, integration and messaging tools, distributed computing primitives, cluster managers, task schedulers, deployment, configuration management, and DevOps are increasingly important in the distributed systems area. And we also need data analytics and machine learning libraries that work well with those distributed systems. And in each of those categories, we have many different technologies, many different tools, each with very different use cases, very different features, attributes, and different level of maturity. So we really need to pick the best tools that suit us for our machine learning pipeline. Traditionally, the data pipeline used to include a monolithic application and often a relational database with full ACID properties representing mutable state. This is very nice for the programmer because it hides many of the complexities, such as concurrency or shared memory from the developer. But they are still there. They're in the database, but they're just handled for us. This does not scale very well with larger throughput or larger data amounts or unstructured data. So sometimes we need to pull those complexities out of the database and handle them ourselves. For those reasons, there were many other architectural patterns developed during the years. The first one is CQRS, where we have the read and write side scalability and technology separated. So the write side is usually a write-optimized database, often an append-only log with very fast writes. And the read side is a denormalized and pre-computed database that is very fast to answer reads for some expected queries. Another typical architecture is batch pipeline, where we have a large scale database such as HDFS, and then many technologies that help us mine the data and query that unstructured large scale database. Lambda architecture is another option where we add a stream layer to fix some of the issues of batch pipeline, which is handling or answering some queries in near real time, at least partially. And the newest one is so-called Kappa architecture or streaming data architecture that stores data in something fast that supports streaming data. The stream is then an immutable source of truth as well as source of data for other systems. The data can be replayed, queried, transformed, analyzed, enriched. It's all done in streaming manner, and it's integrated with other databases. Each of them can have different technology, different data model, and different use cases. The Typesafe technologies I will talk about today fit very well into these architecture types, such as streaming data and event processing. But there's no one-size-fits-all architecture or technology. The common attributes are that all the data are stored. There are multiple technologies in the pipeline for different use cases. Sometimes there's duplication, denormalization. But what we really need to do is to identify the places in our pipeline. We need to identify the features we're expecting, the guarantees, attributes, and we need to pick the best technologies that fit into those places in the pipeline. We built an internal demonstration project, open source project called Mover, which processes streaming sensor data from devices such as accelerometer in a watch, smartphone in a pocket, or heartbeat monitor to classify exercises in a gym in near real time. It uses those types of technologies I will talk about, but the pattern seems to be common for many use cases in practice as well. So the architecture is very similar to what was mentioned previously. The blue box processes streaming data, so we have the mobile device and an Akka Cluster or sharded Akka actors processing the streaming data. We have Akka Streams within that distributed domain, and we store the data in Cassandra database and in Kafka. We use Cassandra also as an event-sourced journal for Acha Persistent. And then the pink box is Apache Spark. We use that for more complex analytics, such as suggestions to improvements to user exercise routine, tracking compliance to exercise plan, or training our machine learning models. We can also train machine learning models in the pink box, and we can send it back to the stream layer serialized, so the mobile device can immediately start using the new model, the new improved machine learning model. At the same time, we need to fulfill SLAs and attributes such as responsiveness, elasticity, durability, and resilience. So we need all those technologies to be distributed and have those properties. So I'll talk about Akka Streams, Spark, and focus on some of the important features they have with regards to large volume data processing. The first option, one option to implement parallel algorithm is using futures. We have all the good things that Scala and the functional programming provides us, such as monadic composition or type system. But still, we must ensure we're handling memory and synchronization properly. Accessing shared state from multiple threads obviously means that they can interleave in more than one possible order, so the result will be incorrect. Akka is an actor framework for truly concurrent and distributed systems. One of the biggest features it provides is it has thread-safe mutable state, which serves as a consistency boundary. So everything that goes through that one actor is single-threaded, so we have consistency just within that one actor. It's perfect for domain modeling in distributed environment. Perfect for distributed state, distributing work to workers, to actors, and for implementation of certain communication patterns. The programming model is very simple. The actor can essentially just send messages, create new actors, and change behavior. But it's often used improperly, so people try to use it as object-oriented programming, but it doesn't work like that. A typical example of an actor, this actor is persistent, so it's backed by an event-source journal. It starts in a not registered state, receives a count command, then it becomes registered. It stores that command or the event in the event source journal, so it can retrieve that state. And then it becomes registered and answers to different set of commands. It also uses Akka distributed data for replication to replicate its state with other replicas in the cluster and share that knowledge. Another typical use case is this. So we have this actor, which serves as a source for Akka streams. So every event or every message received by this actor is turned into an event in streams, and then we can define the flow on that stream of events. Akka is very powerful, is most powerful when it runs on a cluster of machines. It provides very powerful features such as persistence, so backing an actor by an event source journal, sharding, which means horizontal partitioning, or replication, where we have the same entity replicated multiple times in the cluster, and then obviously we need to synchronize them. But distributed systems like this are affected by the very nature of distributed environment and the cap theorem. So there are often trade-offs that are required we need to consider them, such as consistency versus availability, persistence, failures, delivery guarantees, data locality, performance, concurrent updates and conflicts during replication, divergence, or global invariance in the system. One example is time and order in distributed system. So in sequential program, the order of events, there's one total order of events that's always the same. So every time we run the program, the result is exactly the same. But we don't have that guarantee generally in distributed system. Global clock and total order are not possible to have in distributed system. So we're often aiming for partial order and just causality or vector clock in distributed system. Delivery guarantees generally are different in distributed systems. Most distributed systems only provide at most once delivery guarantee, which means messages may be lost. So you need to ensure the message is delivered. You can achieve at least once delivery guarantee, but that means the message may be received multiple times. It may be duplicated. Exactly once delivery is theoretically not possible to achieve. There are some operation semantics that help us to achieve what we need, such as idempotence, which works very well with at least once delivery. Failure detection and recovery is a very interesting problem in distributed systems, because it's very difficult to distinguish between a node failure, a network failure, and just high latency, or the node not responding because of high amount of work, or just doing garbage collection. And components in distributed system fail independently. They can fail anytime, nodes, network, everything. Even large companies like Microsoft or Google have failures quite commonly in their data centers. So this is from a report from Kyle Kingsbury and Peter Baylis. The crucial is how to handle those failures in distributed systems. But as you can see, this is again from Kyle Kingsbury's blog, even mature technologies such as MongoDB, Redis, Riak, Elasticsearch, MySQL even, don't handle those failures properly very often. So they often lose acknowledged writes. During reads, they return writes that should have never occurred, and so on. Akka is a very low-level technology, so we often have to handle those things ourselves manually. Another technology in the Typesafe ecosystem is called Akka Streams. It represents a very different programming model. We have a publisher, subscriber, and stream of events between them, and we apply some transformations to that stream. So for instance, as you can see on this marble diagram, you can transform the stream to square and then filter based on a color. It provides higher level API that can be used to define graphs, reusable components, even with cycles. It's a very convenient, nice way how to declaratively express graphs. So the code on the top is a representation of neural network computation. And as you can see, it very nicely corresponds to the picture in the bottom. So it's a very nice way how to express graphs. But we need to make sure the streaming logic is correct, otherwise we can have incorrect results or even deadlocks and other issues, especially with cycles. In stream processing, usually components can either have bounded buffer, which may result in dropped messages when the buffer is full, or unbounded buffer, which may result in out-of-memory exceptions. So Akka streams provide us a way how to handle back pressure. In Akka, for instance, we would have to do it ourselves. We would have to manage the back pressure somehow ourselves. We can define different back pressure strategies. The graph on the left shows the slowing down subscriber with a bounded buffer, so it starts dropping messages at some point. And the picture on the right is exactly the same scenario, but this time we use back pressure. So the publisher and subscriber, they synchronize their speeds. A typical use case on transformation on streaming data are time series. So in this instance, we're running Fourier transformation on a window to identify frequencies and distinguish between periods of exercise when the user is exercising and when the user is not exercising. Another typical use case is transformation on time series. So we're turning the time series into a different representation of the same time series. So we're using dimensionality reduction and feature extraction. We're essentially trying to represent the time series with less features and with better probabilistic distribution, so it works better with the classifier. In this case, this is symbolic aggregate approximation. But the ultimate goal, really, is to run time series through a trained model and classify what the user did, what exercise it was. So in this case, we have X, Y, Z axes of accelerometer data, and we want the SVM or deep neural network in our case to tell us it was 7 dumbbell alternating curls. And the last technology I'll talk about is Apache Spark. It's an in-memory data flow distributed data processing framework. It handles both streaming and batch computation. It distributes computation using a higher level API. It balances the load, so it runs the computation in the cluster. Most computation to data is fault tolerant. Has very rich programming model, including the main abstraction is called resilient distributed data set. It's fault tolerant, provides means for caching, serialization. Has 2 types of operations: transformations, which are lazy, form the directed acyclic graph, and actions that actually execute that computational graph. Has some distributed computing primitives, such as accumulators or broadcast variables. Has very good integration with other tools. Has very powerful streaming, and has also machine learning and graph processing libraries. But again, there are many of those tools have some subtle important impacts that we really need to understand properly. For instance, accumulators or side effects when running Apache Spark computation. When there's a failure, the computation part of the computation needs to be rerun. So it means that that side effect can be applied multiple times, therefore resulting in something that you're not expecting, even if Spark grants exactly one's delivery for the result. Some computations are very simple to parallelize. So in this case, this is trivially parallelizable. So we just Spark just runs some computations in different threads or even on different machines, and then we just collect the result. But it's not always the case. Some algorithms are very difficult to parallelize using any programming model. So in Spark, we can use this higher level API. We define operations, but it's important to understand that different operations have different semantics and different performance characteristics. So map, for instance, applies some transformation, some function to each element in each partition, which can be very efficient. On the other hand, reduce by key requires so-called shuffle operation. So it shuffles the data between nodes. It requires a lot of network traffic, which is usually very inefficient. Spark Optimizer is called Catalyst. It has multiple phases, so it optimizes the query that you have written. It parses the query to get logical plan that optimizes the logical plan, creates multiple physical plans and uses cost-based optimizer to pick the best physical plan, then generates code using Scala's quasi-quotes, and only that code is shipped and executed. It uses techniques known from relational database optimization, such as removing subqueries, evaluating static expressions, simplifying filters, pushing filters through projections, removing redundant columns in the query, merging projections, and so on. At the same time, it often chooses the best physical execution strategy to utilize knowledge of the underlying data store, so it tries to run the computation as close to the data as possible to avoid network traffic. Currently, there's also ongoing work on explicit memory management, cache-aware computations, code generation optimization, GPU utilization, and adaptive planning. Data frames API, as Matej mentioned this morning, provides more optimization than the strongly typed RDDs because user-defined functions are difficult to optimize. But Apache Flink, for instance, can do many of the optimization with type data because they're using bytecode inspection. So there's really a lot going on behind the scenes when you're running Apache Spark queries. But in the end, it's still programmer's job to implement the algorithm properly using the proper algorithm data structures, just using those primitives and the API that Spark provides. The typical use case for Spark in our Mover project is to train machine learning models. So we split the data into training and testing data set. We run some pre-processing, so normalization, feature extraction, dimensionality reduction. We train the machine learning model. We use the other data set to test it, to optimize the parameters of the machine learning model. We pick the best model, and then we can start using it. We can use MLlib or other existing compatible machine learning library. Spark also provides a nice way to express machine learning pipelines using the pipelining API. So in this case, we create a pipeline, sets ordered stages. We set the normalizer, feature extractor, and then we use linear regression. And then we use this pipeline to train the machine learning model, and the same pipeline to pre-process the data and actually use it. So in this case, we're trying to predict users' next exercise intensity using just linear regression. Another use case we have is to identify similarity between time series to find similar users or label data automatically. So in conclusion, there are many technologies available for processing of large data volumes. The Typesafe technologies are very strong in this area, but what we need to do is we need to identify features, attributes, guarantees, and use cases in our pipeline, and we need to pick the best tools that fit those places in the pipeline. And second, choosing the best tool for our use case is not enough. There are many specific internals and many specific features that may not work as we expect. So it's really important to learn those technologies really deeply and to understand them to be able to implement our programs with sufficient quality and often also correctness. And third, the selection of environment is very important. The environment can be synchronous, asynchronous, or even distributed if we have use case that requires it. Each requires very different way of thinking, theoretical knowledge, tools, and approaches. Thank you very much. And any questions? So the question is if there's any framework to run Akka Cluster on Mesos. I don't think there's any framework, but it's definitely possible to run Akka Cluster, to deploy Akka Cluster using Mesos. Okay, thank you.